This video is part one of two videos in which we'll be exploring geometry and measurement, which in grade 6 includes angles and triangles. The concepts about angles in this first video will be applied to triangles in the second video. Geometry is a big part of what we experience in our world, like in architecture. For example, we see many angles and triangles in the design of this home. So let's first explore angles. When a straight line has a fixed starting point and no endpoint, it is called a ray. An angle is generated when a ray rotates about its fixed point. The center point of the rotation is called the vertex, and the measure of the rotation is the angle. One unit for measuring angles is degrees. For example, this angle is 90 degrees, which is also called a right angle. We usually write degrees using this symbol. We also commonly use a square at the vertex to indicate a right angle. The first key concept involving angles is how to classify them. Here are several angles that can be sorted into different categories of angle. How would you sort them? There are many correct ways these could be sorted, and perhaps you chose a different way. The way shown here is to sort them by their size, as related to 90 degrees and 280 degrees. The group in the top left are angles which are less than 90 degrees. The group in the top right are angles which are greater than 90 degrees, but also less than 180 degrees. We've already classified the lower left as equal to 180 degrees. The bottom right group are angles which are greater than 180 degrees, but they're also less than 360. These categories of angles all have special names. As mentioned before, a 90-degree angle is called a right angle. An angle less than 90 degrees is called an acute angle. If an angle is greater than 90 degrees but still less than 180, it is called an obtuse angle. Because it forms a straight line, a 180-degree angle is called a straight angle. Finally, an angle which is greater than 180, which is also less than 360, is called a reflex angle. In summary, if our initial ray is as shown in green, then we can visualize the size of rotation for each type of angle. Let's apply this understanding of identifying angles to the image from earlier in the video. What angles do you see, and what type of angles are they? You probably found many more, but here are a few of each type, starting with acute angles. Then right angles, obtuse angles, and straight angles, which could be placed anywhere there is a straight line. Reflex angles may not appear directly, but any acute or obtuse angle can be measured as a reflex angle if we measure the rotation in the opposite direction. Let's next turn our attention to how we measure angles. First, we can use these benchmark angles to estimate the measure of some given angles. Here are three given angles. How can you use the benchmarks of 90 degrees, 180 degrees, and 270 degrees to estimate the measure of each angle? Angle A looks like it's about half of 90, so let's estimate about 45 degrees. Angle B is almost 180 degrees, so let's estimate about 170 degrees. Finally, angle C is a reflex angle that is a bit more than 270 degrees, so let's estimate about 280 degrees. While these are good estimates, sometimes we need to be more precise, especially in design and architecture. So we can use this measuring tool, which is called a protractor. Here's how we can use the protractor to measure angle A. First, we need to focus on the bottom center of the protractor. We need to line up the center point of the protractor to the vertex of the angle. Next, we look at the bottom line of the protractor. We need to line this up with one of the rays of the angle. Next, look where the other ray passes through the number markings on the outside of the protractor. Notice there are two sets of numbers. The angle could either be between 40 degrees and 50 degrees, or between 130 and 140 degrees. Because angle A is an acute angle, we know it must be between 40 and 50 degrees. There are 10 degree markings between 40 and 50, so angle A is measured to be 42 degrees. This verifies that our estimate was a reasonable one. Let's apply the same process to measure angle B. Keep in mind that this is an obtuse angle, so we need a number greater than 90 degrees. The angle is between 160 and 170 degrees, so its measure is 163 degrees. Notice that if we align the bottom of the protractor with the other ray, we still get the same measure. Angle C is a reflex angle, so it is bigger than 180 degrees, which means it's bigger than the protractor can measure. How could we still use the protractor to figure out the measure of the reflex angle? The full circle of rotation is 360 degrees. If we subtract the acute angle, then what remains is a measure of the reflex angle. The acute angle measures 75 degrees, so the reflex angle can be calculated by subtracting 75 from 360 degrees. So angle C has a measure of 285 degrees. We can also use a protractor to construct an angle. As an example, let's construct an angle that measures 112 degrees. First, start with a ray going in any direction. Next, line up the protractor. We can see 112 degrees in two locations. If we use the one on the left, this produces an acute angle. But 112 degrees is obtuse, so this is not the correct one. Instead, we should choose 112 degrees that shows up on the right. And thus we have constructed a 112 degree angle. Now let's continue our exploration of angles by looking at polygons. Each of these shapes is a polygon. A polygon is a closed figure whose sides are straight line segments. Let's begin by looking at triangles. Though all of these triangles are different, there is something with the angles that all three of these triangles have in common. Take a moment and see if you can figure out what is the same about these triangles. If we take the sum of the angles in each triangle, we get 180 degrees for each of them. So generally, the sum of the interior angles of a triangle is 180 degrees. Here's a quick visual proof of this concept. Suppose we have any triangle. Let's name its angles A, B, and C. If we make copies of the triangle and rotate them, the three angles come together to make a straight line, which is 180 degrees. So the sum of A, B, and C is 180 degrees. But what about other polygons? Let's first look at a four-sided figure, which is called a quadrilateral. Notice that we can divide the quadrilateral into two triangles. With that in mind, how can you figure out the sum of the interior angles of the quadrilateral? The top triangle has a sum of 180 degrees, as does the bottom triangle. So overall, the sum of the interior angles of the quadrilateral is 2 times 180, which is 360 degrees. Can you use a similar strategy to determine the sum of the interior angles of the other polygons? We can divide up each polygon into triangles. The sum of the interior angles of each polygon will be the number of triangles times 180 degrees. Notice that for each polygon, the number of triangles is 2 less than the number of sides. So we can generalize for any polygon. We can determine the sum of the interior angles of a polygon by subtracting 2 from the number of sides and then multiplying that by 180 degrees. Let's apply what we have learned about angles and polygons with a couple of examples. The sum of the interior angles of a polygon is 1,260 degrees. How many sides does a polygon have? Take some time to see how you could solve this problem. From our general concept, if we divide 1,260 degrees by 180 degrees, that gives us 7. So 7 must be 2 less than the number of sides of the polygon. So the number of sides of the polygon is therefore 9. We can check our answer by sketching a 9-sided polygon. Dividing up this polygon into triangles, we see that there are 7. Our next example will consider how angles are an important part of artistic design. Consider this design made up of shapes. Let's look at one of these shapes. Some of the angles are given, but we don't know the measure of these missing angles, A and B. How could you determine the measure of angle A and the measure of angle B? The black shape is a hexagon, so it has 6 sides, and the sum of the interior angles of a hexagon is 4 times 180 degrees, and that equals 720 degrees. So if we add up the angles in the hexagon, the sum will be 720 degrees. This means that angle A plus 640 will be 720. So angle A must be 80 degrees. For angle B, let's look at the red triangle. The sum of the angles in the triangle is 180 degrees. But we don't have enough information. We need to figure out what measure the purple angle has. Notice the straight line, and that the purple angle plus 80 degrees more would give us 180 degrees. So this angle must measure 100 degrees. Now we know 2 of the angles in the triangle, and they add up to 120 degrees. So the third angle B must be 60 degrees. This video addresses several learning standards in the Mathematics Grade 6 curriculum. This big idea emerged frequently as we described and measured angles. In content, we looked at angle measurement and classification. In their classroom, several curricular competencies may emerge as your child learns about angles. There's a lot of mathematical vocabulary developed to be able to describe angles. Reasoning and logic were used to classify angles, and these mathematical ideas were applied to solve problems. One way to measure angles is to estimate using benchmarks of 90 and 180 degrees. Finally, we looked at how angles connect to the real world, like in architecture and in design. We hope that you found this video valuable in helping you support your child in their learning about angles. Please watch Part 2 on triangles, to learn how the concepts of angles help us to classify and understand the types of triangles. Also, be sure to check out the other titles in this series.